Okay. All right. So I guess first of all, any questions about this one that you guys had before we move on? So what was the one that increased the most and that we don't really expect to be a limiter of VO2 max? Which one was it? Do you remember? Ventilation. Yeah. So that was our most increase. And then the other one that we typically expect to be the major limiter of VO2 max is what? Stroke volume. There we go. So the limiter. Ooh, that's the limiter. There we go. Okay. Yeah. So the most increase, major limiter. Yeah. So those are the two key ones there. Okay. All right. Then when it comes to these equations here, so first of all, just the equation for RER. How do we get RER? What do we need to know to have RER? Okay, that's part of it, but before that, actually, this is what is RER? How does the metabolic cart give us RER? What is it? What two numbers does it use? There we go. Yeah, and then how does that? So then the equation is the CO2 divided by VO2, right? So it's just volume of carbon dioxide breathed out versus volume of oxygen that was consumed. Okay, and so the oxygen one, we don't necessarily care how much oxygen is being breathed out, right? We care how much is being consumed. So just if you think about it, that one's actually calculated based on what the inspired oxygen was, right? Because we're only measuring expired air with that device, not inspired air. So by knowing about how much oxygen was in the air to start with, and then how much the person breathes out, it calculates that number. Right. Okay. So that's our RER number, CO2 over O2. As you guys said, the glucose one is right there. Right. So that's what with a mole of glucose, it takes 6 moles of oxygen. We get 6 moles of CO2. That gives us our 6 over 6. So an RER of 1.0. Okay. The fat one is here. Right. Palmitic acid, 23 oxygen, 16 CO2s. And so that's the 16 over 23. That gives us about 0.7. Okay. So as you guys commented in your labs that you turned in last week, low intensity exercise, the RER starts lower, right? It should be closer to 0.7 if somebody's just like walking real slow. And then as they start to, when the intensity starts increasing, and we saw this in Ilse's numbers, right? The RER at 3 miles per hour was like, what was it, like 0.8 or something, 0.84 or something, somewhere around there. And then it went up to like 0.92 at 4 miles per hour or something, and then went up to about 1.0 when she was running at 6 miles per hour. Okay. So then the real question, so that's showing us that we shift from fat usage to carb usage when we start exercising more intensely. And so then the question is why? Why does that happen? Why do we have to shift over to carb usage when we exercise more intensely? What did you guys write in the lab? I know quite a few of you had an answer for that. Emmeline, what'd you say in the lab?
I don't remember. It had to do with the buffering system and like how CO2 increased, it would, affect the rest of that.
Okay, that's kind of the answer to the next part of this question, which is a good answer for that part. But why does our body have to go, why does that RER have to go from 0.7 up to 1.0 when we start exercising more intensely? Meaning, why do we have to shift to carbohydrate burning to keep up with intense exercise? It's because carbs burn faster than fats, right? It takes longer to burn fats. And so we just can't keep up with the ATP demand of running hard or cycling hard or something like that if we're using fat, because fat just takes longer to metabolize. Okay, and so this is why with the crazy no carb or low carb craze that's out there right now, that if you're an athlete that wants to be able to push themselves hard and you're not taking in carbohydrates, it just doesn't work, right? And this is primarily because we have to switch over to the glycolytic system too, right? And if we're not eating carbohydrates, we drain our glycogen out of our muscle, and when we start shifting to more intense exercise, even higher than getting up to 1.0, we have to get up above that too, and that has to do with lactic acid buffering, right? That we'll talk about in a sec. But the research shows pretty clearly that low carb diets, people can do okay at around maybe 50 to 60% of VO2 max. But when it comes to anything above that, maybe like 70, 80%, 90%, which is what we do when we sprint, when we run up a hill, they just can't keep up anymore because they don't have as much glycogen in their muscle because they haven't been taking in carbohydrates. So we need that glycogen to do higher intensity stuff. And so we need to eat carbohydrates for that. Yeah, so, but before we even get above 1, we're shifting from 0.7 up to 1. And that's not necessarily using the glycolytic system. It is some, but it's also just shifting over from fat to carbohydrate usage using the oxidative system. Okay. And then once it gets really intense, then we really need a lot of the glycolytic system, right? And then we start making a bunch of lactic acid. And then Emlyn can tell us about that equation. What equation is that?
It's the HCO3 ion plus a proton into H2CO3, which turns into water.
Yeah, perfect. Right. So that's our bicarbonate buffering system. We got bicarbonate right there. We got a hydrogen ion. This is the one that would come off of lactate. Right. Lactate would release this guy. We've already got bicarbonate floating around in the blood. That hydrogen ion would bind to it. When it does that, it turns into carbonic acid, which is this one. And then carbonic acid can dissociate in CO2 and water. And we breathe this CO2 out. Right. That comes out of our lungs. And so it's always interesting to me that we deal with the problem of too many hydrogen ions by getting rid of CO2, which doesn't even contain hydrogen, right? But if we get rid of that CO2, we can't reverse this equation and remake that hydrogen ion. It doesn't work, right? So here we have 6/6 giving us 1.0 with pretty intense exercise, but now we're adding some extra CO2 to that 6/6. Right, that comes from that buffering equation, and so that's what drives our RER up above 1. Right, and so when we do the max test on Wednesday, who was it? So they were going to do that. Was it Benny that said he was going to do that? Does anybody remember who volunteered? Was it Alex? Okay, that's right, because he's not. Yeah, that's right, Alex. Okay, and he will be back for that. Yeah. So when we do his max test, we'll see this. We'll see his RER go up and up and up. And then actually one of the criteria to decide whether or not somebody reached a true max is did their RER get above 1.1 or 1.15, kind of depending on what you use. And that's just like kind of a sign of that they really push themselves hard and they push themselves into acidosis a little bit. Right. So that's all of that. Okay. Questions on those? All right, so this equation here, so we got the end diastolic volume, we got end systolic volume, we got resting heart rate. So the equation for cardiac output is what? Stroke volume times heart rate, okay. We don't have stroke volume here, so we need the equation for stroke volume. What's that? Okay, EDV minus ESV. Okay, so we can calculate that one. So that's 150 minus 50. So we got 100 mils at rest for stroke volume. Okay, so we got 100 mils times the 60. Okay, so this gives us 6,000 milliliters per beat, really, because heart rate is really beats per minute. Okay, yeah, 6,000 mils per minute is really what it is, right? Not per beat, but per minute. Okay, and then we just need to convert that to liters because cardiac output is pretty much always expressed in liters. So we would just move that decimal place 3 to the left, and so we get 6 liters per minute. Okay, is that what everybody else got to? Okay, all right. So that's our resting, and then we can look at our maximal here. So same thing. Let's calculate our stroke volume first. 220 mils minus 20 mils. Oops, mils. Okay, so then we got 200 mils there, right, with a heart rate of 180. So we got cardiac output equals 200 mils times 180 beats per minute. Okay, so then we multiply those together. What does that give us? It was a little harder to do in my head. Say it again, John. 36,000, okay. 36,000 mils per minute. Okay, and the reason these cancel out, so BPM is beats per minute, right? That's the stroke volume number. Or sorry, that's the heart rate number. And then the stroke volume one is mils per beat, right? So we got a beat on the bottom, a beat on the top. So those cancel out. We end up with mils per minute. Okay, so 36,000, we'll move that 3 places to the left. So we end up with 36 liters per minute. Okay, so we went from 6 liters per minute to 36 liters per minute. Okay, so a 6-fold increase in cardiac output from Rest-O-Max. Okay, so then that kind of sets up what we're going to do for the rest of the class, which is look at how these things change. Right, so we'll start out with the heart rate one. So that's team 6, I believe. You guys ready? Okay. Does one of you want to airplay on there with your, yeah, okay. So yeah, so you should just be able to hop on there. Yeah, go ahead.
About heart rate, especially context to how it so first of all, changes in heart rate are due to changes in cardiac output demand. So it's done to accommodate for those changes in cardiac output needs. So it would indicate that the body would be changes in temperature, differences in blood gases, that kind of stuff. So without the influence of the nervous system, heart rate is set to about 100 beats per minute, and that's because of the autorhythmicity that we put that essay in. But so the body will.
Sorry, I forgot. I'm gonna put this right.
Sure. So the body will take steps to increase heart rate to meet the cardiac output demands, and it'll do it in this order. It'll decrease parasympathetic activity. That will increase to about 100. The cardiac accelerator nerve will be used to give that sympathetic nervous feedback, and then catecholamines will be used to increase it to maximal levels. And so this is the neural pathways that are used. I'll talk about a parasympathetic pathway that's used to influence heart rate. So the signal is sent from the medulla oblongata in the brain through the cranial nerve 10, which is the vagus nerve, to the heart. And at the heart, it will secrete acetylcholine, which will its effect on as we noted, is to hyperpolarize the resting potential. So if it was at a particular level, then it will decrease it. So it takes longer for it to get up to threshold to shoot the action potential. And so this effectively decreases heart rate.
Okay. And then for the sympathetic influence, there's 2 separate pathways that we could use to get the sympathetic, I guess, reaction. So the first one is the action is sent from the medulla oblongata to the heart via the cardiac accelerator nerve, and then norepinephrine is released, and the cardiac cells depolarize, and that's going to increase the heart rate. And then the other one is the APs are sent from the adrenal medulla, and that causes epinephrine and norepinephrine to be released, and the cardiac cells depolarize, and then that will also increase the heart rate.
So when talking about the parasympathetic withdrawal, so it's at rest. At rest, the parasympathetic nervous system controls heart rate. And in anticipation of exercise, this is Tara's slide, so she kind of like outlined the pathway of it. So anticipation of exercise leads to vagal withdrawal, so the removal of parasympathetic tone. And then that leads to a decrease in action potential frequency on the vagus nerve, which then decreases acetylcholine release and thus decreases hyperpolarization of cardiac. So when you move on to like the sympathetic stimulation, it's kind of like the opposite of that. So you kind of get that fight or flight response. And the amygdala, which senses that stress, releases hormones to stimulate the hypothalamus, which activates the sympathetic nervous system to elevate that heart rate. And like, and okay, yeah, when you activate the sympathetic nervous system, it goes back to the pathway we just talked about before. And it leads to the stimulation of the adrenal glands to release the choline. And for sympathetic stimulation, it redirects blood flow to the necessary muscles and draws the blood away from the muscles we don't really need at that moment. And on top of raising heart rate, it also increases heart contractility, increase that force.
So then when the capital is released, that kind of gets the heart to lack of level. And what happens is hypothalamus triggers the adrenal to increase levels of epinephrine and norepinephrine, so that the heart can increase to the maximum beats per minute. And if those two work by increasing the contractility of the heart, by increasing the by calling the calcium in blood to allow the heart to still.
And usually what I'll do after the team goes is just kind of show you the slide, the way I took notes from their thing. So this is pretty much what I wrote down from theirs. Yeah, this is exactly what they had, an order of things here. Right, they had the ENS pathway there, and 2 SNS pathways there. Right, so we've got the cardiac accelerator nerve side, the adrenal medulla side. That's just my shorthand notes of everything they just presented. So, yeah, the only thing I'll say just to make sure, and you guys said this, but just make sure that you guys do when you do your concept maps is to do, when you talk about this pathway, make sure you're talking about it decreasing, right? So you could have the pathway there, but then maybe you'd have something like decrease AP frequency or something here, right? So then it'll be decrease acetylcholine release, right? Then it would be decreasing the hyperpolarization, right? So then this here would be actually increasing the heart rate by doing that, right? So it's just kind of okay. All right. Any questions about the heart rate one? Okay. All right. And then, yeah, so then we've got team 5, right? Is that you guys for the preload one? Yep. Yep, cool. All right. Somebody gonna airplane? I'm gonna actually change the microphone to this other one.
How do you?
Oh, yeah. You discussed it.
You got it. You got it. This is for. Why did you do that? Now, what's your school email? B. Sawyer?
Yeah.
Is it true that after we graduate, we don't get to use our email? That's so weird.
That's why I'm like, that's stuff that
Oh, that's a good idea.
yeah, a lot of things. That's I already have. Don't do this and everything.
I'll be willing to put it on, to be honest. Because I just have lots of time all the time.
I don't do that.
I was like,
Okay.
Okay, so our section of preload. Basically, a preload is the blood in the left ventricle before the heart beats. This is also known as like end-diastolic volume. We measure it in, oh, sorry. The equation is VO2, heart rate times systolic volume, and then the arterial venous difference and oxygen, and then it'll be the stroke volume. It's determined by venous return, so the blood returns to the right atrium. More blood in the ventricle means that you'll have an increase in stroke volume, since stroke volume is in diastolic volume minus systolic volume. And then less blood in the ventricle means a decrease in stroke volume. Elasticity of the heart. So the more that we stretch it out, the harder the heart bounces back. So the dictating factors of blood returning to the heart is controlled by the muscle pump, or changes in that, respiratory pump, one-way valves, pulse wave, sympathetic tone, so like vasoconstriction and the reservoir for blood in the veins, and the changes. Body position, so if you're sitting, standing, running, walking, and then, I've never said it correctly. Valsalva maneuver. Valsalva maneuver. Because that increases your pressure. Basically.
And so maybe explain what you have the changes next to it. You didn't explain that part.
I didn't make the slide.
Okay.
I was presenting what they gave me.
That's fine.
I think what she meant by that was like if you're exercising and it increases, and it's gonna like affect other parts of your body as well.
Okay, so with an increase in preload, you also have an increase stroke volume, or stroke volume, sorry. And then the factors that increase the preload during exercise include the blood volume increase, sympathetic tone, boost of catapulting, and then increase in muscle contact, which is on the thing. So with this diagram, I mean, it has a direct relationship between the stroke volume and then the solid volume. So if one increases, the other also increases.
Any questions?
Go back to the other slide, Jim, real quick. Yeah, okay. Any questions for this guy? Okay. All right, good job. Okay, yeah, so. So yeah, I didn't get to write everything down I wanted to, but I'll finish it. Yeah, obviously measured by EDV, like this said, venous return. The part that I was, that Kaya was getting at probably with the ones that change. This would be what you want to say in your concept map too, which would be, these are all the things that kind of determine venous return, right? So these things connect to venous return, but some of those don't change when you go from resting to exercising, so they don't change your stroke volume, right? Because that's kind of what we're looking at for the concept map, is how does your stroke volume change? How does it go up from rest to max, right? So body position doesn't really change, right? The valves don't change, they're always there, right? But the one she had change next to means that they actually work more when we're exercising, right? So the muscle pump does because we're contracting muscles more and harder, right? So pumping more blood that way. The respiratory pump also because you're breathing harder, breathing faster, right? Sympathetic tone, like May said, this mobilizes blood in the veins. Right, so by squeezing down those veins, that brings a bunch of blood back into circulation, right? And then it also just overall increases our blood pressure. So blood's just moving through the body quicker. So more of it's going to come back to the heart when we do that, right? And then the pulse wave is going to increase too. That's just your pulse in your artery hitting on your veins and squeezing those veins down a little bit. So those are the four that are really going to change when you start exercising to help you increase that end-diastolic volume up here, right? Yeah, and then I'll just hone in on the Frank Starling mechanism. On the one slide, there was something about it, which was really just the elasticity of the heart. Right, so the more blood we put in, the more it stretches out, and then it is elastic, so it bounces back. So that makes more blood come out. Okay, but that was one. What else was there? There was actually three factors there. Does anybody else remember the other two? So one's the elasticity, it bounces back harder. Two is just like in skeletal muscle, we had that length tension relationship, right? So we get increased actin, myosin binding. Right, so just like in skeletal muscle, we're stronger right here than we are down here, right? Because some of those myosin heads aren't touching the actin when you're fully lengthened. Okay, and then the other one, this was part of what Sophie taught that day, and then the other one was just that when we stretch out our sarcomeres in our heart, the affinity of troponin for calcium increases. And that's just like a structural thing with the troponin protein. When we pull on it, the binding site for calcium, it just becomes a little bit more available. So that means that the calcium that comes in will make more actin myosin binding as well. Okay. So the reason this is important here is because it's not only that we get more stroke volume because we put more blood in, that is a big part of it, but the other part of it is there's some physiology of the heart that acts a little bit, it acts a little bit more efficiently when we fill it up with blood, right? Because of those three factors there. Does that make sense? Go ahead, Lisa. Yeah, so it's kind of a tricky one because contractility is the strength of the heart contraction. And so there's definitely overlap here in a way. But when we think about what changes contractility, we really just think about the one that you guys will probably talk about, which would be sympathetic nervous system, right? But putting more blood in the heart also makes it contract harder because of these three things. So it's a little bit of overlap there, but these ones are directly related to the preload, which is how much blood we put in the heart, whereas the other one is controlled outside of how much blood's in the heart completely. Yeah, good question. Other questions on that? Okay, so next one is going to be team, which one is this? Team 4 that we're at? Yeah, okay, you guys ready? Yeah, you guys can come on up whenever you're ready. Maybe just switch oh yeah, there's. There you go.
Okay, so we have afterload.
So factors of afterload is ventricular contractility, and then the second one is aortic or pulmonary artery pressure. Okay, going into that a little bit more, afterload, it's just after the ventricle has filled, it's the pressure that the heart needs to overcome to pump the blood out of the artery. So it's determined by blood pressure, and the equation we can use is the mean arterial pressure, and mean arterial pressure is just the average pressure exerted as blood is being pumped in and out. And the equation for that is 2/3 times the diastolic blood pressure plus 1/3 systolic blood pressure.
Okay, so for changes with exercise, at rest, the normal blood pressure is around 120/80. But as exercise increases, the systolic blood pressure, we see a really big increase in that. So it goes from the 120 to around 160 to 180 beats per minute. And then the diastolic blood pressure, it either doesn't change or it decreases slightly from anywhere around like 80 to 78 beats per minute. So because of major increase in systolic blood pressure, the afterload increases with exercise.
So in relationship to stroke volume, there's an inverse relationship. So when you work out, your blood pressure goes up, and that's more resistance your heart has to go against to push the blood out of the ventricle. So this is going to bring up the end-systolic volume, close the gap between ESP and stroke volume.
Okay, any questions? Yeah, thanks, guys. It doesn't let me kick you off, Erica, so that's okay. So if any of you guys get here before me one day, you could just take over the Apple TV and I couldn't teach. You guys could just hold me hostage. And just go back to that mirror and then click on the screen again. And then use. Got it. Yeah, so that afterload one's very simple. Like I said, and I like how you described it with saying that it decreases our stroke volume, and then that results in actually an increase in systolic volume, right? Because we leave less blood in the heart, or sorry, leave more blood in the heart because the time that valve is open is less. Right? So yeah, I think that's perfect. Measured by mean arterial pressure, afterload goes up with exercise. This slightly fights against our increase in stroke volume. Okay, so when it comes to those three, preload, afterload, contractility, we've heard about preload so far. That one's helping. Afterload's fighting us a little bit, and then we'll see in a sec. Contractility helps us as well. But I think we're going to save contractility for next time because Alex will be back. But we can go ahead and do the one after that. I think that team's ready, right? The AVO2 difference team. Where are you guys at? You guys are ready? All right. Yeah, and then, okay. And then you guys probably didn't expect to go there. Okay. All right, let me see, because there's a couple slides in here that I was going to do that what's that? Oh, just, yeah, they got their parts, I see. Yeah, hold on one sec. There's a couple slides that I didn't assign. Let me see what those are, and I could do those real quick here. Okay. Oh yeah, so you guys started at slide 13, right? For the AVO2, yeah. So we can actually do these couple slides here together, and then you guys do 13. Yeah, got it. Okay, so Yeah, so one thing we can do here with this graph, we'll talk next time about how contractility increases and how AVO2 difference increases, but we can just calculate it here first, okay? So when we look at this, as you can see, the mixed venous content is this kind of purple graph, right? And then we have the one that we really want to look at is the arterial content, not the capacity, so the blue one, okay? So if we want to calculate this A minus VO2, what would our A be there? For resting, so what would the arterial content be, and then what would the venous content be for resting, just by looking at the graph there? Maybe somebody raise their hand. Anybody? So this is the oxygen content on the y-axis, right? So we're just looking at this point versus this point. Go ahead, Tammy. Yeah, well, so yeah, maybe something like, you're saying like 17 or something? Yeah, 17, 8, yeah, probably, yeah, maybe let's call it 18, something like that, 17, 18. You can't tell exactly there, right? But so that's our vein, that's our arterial one, right? So let's just call it 18, and then we've got 12, right? So our AVO2 difference at rest is 6. There's 6 mils of oxygen per 100 mils of blood is the way that that's usually calculated, meaning that you would draw 100 milliliters of blood, and then just there's 6 of that 100 milliliters of blood, there's 6 milliliters of oxygen in it, right? That's the way it's calculated. And then all the way out here at maximal exercise, we've got this one. It didn't change much at all, right? Maybe just a tiny bit. You see a tiny little slope in that line. What would cause that tiny little slope in that line? There was a question on the IRAT. Remember when we squeezed? Yeah, go ahead, John. Okay, because of, yeah, perfect. Because we squeeze a little plasma out when we start, when we increase blood pressure. So yeah, so we have just a little bit more carrying capacity of oxygen in the blood, but not much. I mean, we would probably still call it about 18 there. It didn't change much. But then this one went way down all the way probably to about, we'll just call it 4 to make it easy. Okay, so that one went quite a ways down. So now we're talking about 14 mils per 100 mils. Right, so we changed from 6 to 14, right? And so then if you're asked the question of which one changes, is it the arterial side or the venous side? Which one is it? The venous side, right? For sure. Yeah, so definitely the venous side is the big one that changes. Okay. And there's a bunch of reasons for that. And the team will tell us about that next time. Team 2 will tell us about that next time. But one of the biggest reasons is this, right? We can also, we change how much blood flow we send to muscle by just an incredible amount, right? We go from 15% of our cardiac output going to our muscle at rest up to as much as 85% of our cardiac output of going to our muscle. So that's all about vasodilation, right? So that's a huge part of this, is we're just sending more blood to the muscle. So what we're thinking about with this is is thinking about how much blood we're sending to an area, and then we're thinking about how much blood's in places where we can pull it out, like in capillaries, right? And then we need to also think about what's using up that oxygen, because that's how we change the concentration gradient and make more oxygen get pulled out of blood, right? So what's going on inside the cells, what's going on inside the capillaries, what's going on as far as blood flow goes, are the things we kind of want to think about there. But that team will fill us in on that next time. Okay, so Wednesday's class, we'll meet in the lab again. Okay, so come ready for that. Just show up right at the lab and we'll do the VO2 max test. Okay, and then Friday we'll come back and finish up these notes. All right, see you guys.